All right, friends, welcome to calculus. This is our third lesson, but this is the first day we're going to consider a concept in calculus, which is limits. So that's today's challenge, and let's dig right in. So we started off with a review of these concepts today, so please check prior videos if you need any support with those ideas, but the gist is here we're going to multiply top and bottom by the conjugate, and that will be root x plus 1 minus 3 top and bottom, and here we're going to multiply by root x top and bottom to rationalize the denominator, and you can slide there to get there. So that's all that we're going to do there. Let's dig in right away to limits. And so I'm going to assume that all this is new to you and you don't know that. So the first thing that I'd like to do is define what a limit is. If you're in class, we went through quite an intro, which I am going to do a brief intro on. Okay, so this is the concept of a limit. First off, just so you can see its power, and here's the idea. The concept of a limit would be this, or how we could use the notion of a limit and would be this. Let's suppose we're trying to figure out the perimeter of this circle with this triangle. Obviously, we'd say that's a bad choice. It's not an accurate representation. But that doesn't mean we can't use other shapes to learn things about a circle. For example, we know that the equation for the perimeter of a circle is 2 pi r. Now, in this case right here, the radius of this circle is 1. So we already know what the perimeter should be. We know that 2 times pi times 1 would be approximately 6.28. Okay, so hold on to that just for a second as I define what a limit is sort of from a mathematical standpoint, or why we might consider this. Right here, this number here, 5.19, is the perimeter of this triangle. Obviously, those are not the same, but if I increase the number of sides of the triangle, I notice that this value here is getting closer and closer to the actual area. In fact, if I made this a 100-sided polygon, we can see that we're getting really close to the area of a circle. In fact, if I made it 1,000 sides, we'd say this is the area of the circle. But then I come back and ask, is this a circle? And of course, to our eyes it is, but mathematically it's not quite a circle. It's actually a 10,000 sided polygon, which is basically a circle, but not. Okay, so again, what we could do, so we could say as n, or the number of sides, gets bigger and bigger and bigger. As it gets bigger, we're going to get closer and closer to the actual perimeter of the triangle circle. So the concept of a limit is that we can have things approach certain values that then allow us to make decisions about things that aren't exactly what they are, but in a sense it allows us to talk about them. Okay, so we're going to get started with a real quick introduction, and here we go. So a limit. This reads the limit as x approaches 5. So as x approaches 5, there's x equals 3, 4, and as x approaches 5, what is the limit? As x approaches 5, the limit is, you can see that it's 4. It's right there. A limit is a y value. You might want to write that down. So the limit is a vertical value. It is a y value. So this is implied when we calculate the limit. The limit is a y value. Okay, now this one, you might not know what that hollow dot means. It means that there's nothing there. It means that this function does not exist at 5. It exists before 5, but not before. So we could say that x is less than 5, but does not equal 5. So if we said, what does the function equal when x equals 5? We'd say nothing. But if we said, what does the function equal as x gets really, really close to 5? So here's x equals 4, 4.5, 4.99999. And as we get closer and closer and closer to 5, you can see that this function is getting really, really close to a certain number. And that certain number, of course, would be 6. Okay, here's another thing that a lot of people don't know. 1 divided by 0. A lot of people think that the answer to this is 0. It's not, and it's not 1 either. Let me help you see that. Another way of saying this is, how many times does nothing go into something? Nothing doesn't exist, but nothing is, at the very least, you could agree that it's so small that there's nothing there. I'll show you what I mean. 1 divided by 1/10 is 10. 1 divided by 1/100th is, by 1,000th is 1,000. 1 divided by 100,000th is 100,000. You can see the smaller the denominator gets, the larger this value gets. So when you type in 1 divided by 0 on your calculator and it says error, the reason it says error is because it can't compute it. Like 0 goes into something infinite times. The graph of 1 over x, for what it's worth, looks like this. Okay, so if we plotted this in Desmos or made a table of values, it would look something like this. So as x goes to 0, notice that this red curve is going to, in positive infinity, it's also going to negative infinity. So this one is undefined for a number of reasons. One is that it's going to infinity, and two, it's going to two different infinities. So it's really undefined. Okay, so let's look at this just graphically. So we could say evaluate the limit as you look at this graph. As x goes to 2, here's x equals 0, x equals 1. As x gets really close to 2, I can see that the limit is 4. I can see it right there. It's on the graph. Now let's look at this one. Here's x equals 2 here. As x goes to 2 here, I can see that it's going, oh, as x never gets there. Oh, this is undefined. As x approaches 2, we'd say that there's no limit. Okay, now here we'd say this is a graph. We notice that at x equals 2, there's nothing there. If you were in grade 11 and said, what's the value of the function when x equals 2? You would say there is nothing there. It is undefined. However, that is different than when we're talking about a limit. And a limit is saying as x approaches 2 from this side and from this side, and it would be better actually for me to go horizontally because that's the x value. But we can see that it approaches something. That has a height of 4. It's right there. Okay, so again, there's nothing there, but that doesn't mean we can't approach anything. So for example, if x equaled 1.999 and we continue this forever, don't you think that we're not never going to get to 2, but we're so close to 2 that we can say that this sucker approaches something, which it does, and in this case it is 4. Okay, so now let's look at this guy. Now we're going to compute limits from an equation. As x gets really close to 2, what's the value of this function? So you have to think, in many ways, you're just substituting that in. But 1.999999999 plus 2 is, of course, it would be 4, wouldn't it? It would. We can see that. Okay, it's not 4, but it's so close to 4 that we can say that it is. That's the idea of a limit. Now, let's look at this one. As x goes to 2 here, we're going to have 1 over 0, and we know that that's going to be undefined. So when you place 2 in here, it is undefined. So if we have 1 over 0, it's undefined. All right. This is going to be the sort of the last review question before you're going to try some challenges. Watch this. It would be really tempting here to say that the limit here does not exist, because when you put a 2 in right there, you're going to have a 2 minus 2 is 0, and you're going to think, oh, I have something over 0, so it must be undefined. But not quite, not quite. Look at this. You guys know this. You know that another way of writing this would be just to cancel these guys out, right? Because you can. Those two are the same. This is multiplication, so we can subtract, we can cancel them out, which means it would leave me with this thing. The graph of this line looks like a straight line, and notice there's an empty set at x equals 2, and that makes sense because x can't equal negative 2, and that's true. So when x goes to 2, is there a limit? And there is. We can see it. It's right there. It's getting really close to 4. So the limit here would be 4. That's how it is. Okay, so just a hint, before you try the next few questions, know that before we make our decision as to whether something has a limit or not, what you first want to do is plug in a number to see if the denominator is in fact 0. If it is, then what you're going to do is try simplifying by factoring, simplifying fractions, or rationalizing the numerator and denominator. So here we go. So in this one, there's nothing to simplify, so we put 4 in there and we'd say it's undefined, and it is. And the graph of that looks something like this, and as x goes to 4, it goes like that. You're not required to know what these graphs look like, but I add that so that you can understand what we are doing, what it looks like. Okay, and so this guy right here, algebraically, if you put -4 in here, there's nothing wrong with that. It's going to be 1 over -8. It has a limit of -8, and that's exactly what's true. There it is right there. When x equals -8, it actually equals something. Okay, so now what we're going to do is we're going to play around with this one. It will be tempting to say that there's no limit here. Okay. Oh, by the way, pause the video. Give this a try first. Okay, so I hope you pause the video. We're going to put 2 in there. We're going to have 2 squared minus 4 is 0. We're going to think it's undefined. That may be true, but it might not be. I don't think it is. Watch this. Is there another way of writing the top? Is there another way of writing the bottom? And of course, the answer is yes. We could factor the top to go x minus 2, x minus 1, x minus 2. Oh, do you notice that those two are going to cancel? And they do cancel. Okay, so we can cancel those. And now what's going to happen is as x goes to 2, I'm going to put a cute little 2 right here and a 2 here, and we're going to have 2 minus 1 is 1, and that's going to be over 1/4. Okay, so what does that actually mean? Here's what it means. If we were to graph this, and I do not expect that you know how to graph these yet, I put this here only so that you know what it happens to look like. Okay, this graph looks like this black curve here. Okay, it's a rational function. Notice that there's going to be an empty set at 2. Why is that? Because we know here that x can't be 2 or x can't be negative 2. The first thing we notice here is x can't be negative 2 or positive 2. As this curve comes through this, notice that it's going to get really close to that empty set but never get there. So when we substitute 2 in here, we're saying that the limit is 1/4. It actually approaches something. Okay. If the question had been what is the limit as x goes to negative 2, that would have been a different answer. It would have gone, oh, it's going to positive infinity and negative infinity. Okay, let's take a look at the next challenge. Okay, this guy right here, it says determine the value of, that should have said of the limit. Okay, so same move here, friends. We're going to simplify by factoring first. And so I think we're good with that. We know how to factor a difference of cubes. And notice here that we have the x minus 2 times blah, blah, blah. And then we have an x minus 2 times x minus 1. These two here are going to cancel. Notice that there'll be two restrictions, that x can't be 2 and x can't be 1. When we substitute the 2 into this, remember this will cancel. And then we'll just have 4 plus 4 plus 4 over 2 minus 1. So the limit is 12. And that's exactly what we get. And we can see when x equals 2, again, you don't need to know that this function looks like this, but it does. And this is what it looks like. So this function exists everywhere except at x equals 2. But as x approaches 2, we can see that it approaches a y value of 12. I am going quickly. I'm out in the hallway and kiddos are going by, so I'm trying to do this quickly on my spare. Okay, this one's going to cause lots and lots of trouble. So let's kind of take a look at this one. So here we go. This one says calculate the limit as x goes to 0. So what we're going to do here first is we are going to put the 0 in. And notice when I do that, I'm going to have something over 0. I'm going to be tempted to say that it's undefined. But what we're going to do is there's something we can do here. What I'm going to do is I'm going to multiply top and bottom by something to make this, to sort of simplify the fraction. And I hope you look at that and recognize that that fraction is not simple. Okay, it's not in simplified form. Because I'm doing all this with a mouse, I'm not going to write down all the details here, okay? So this should be well, fine, I'll do it. X plus 3, this is a pain to use a mouse here. Okay, so when I expand this out, notice that this is going to multiply to this term, and it's going to multiply to this term. When we do that, on this first bit, notice that that's going to cancel out with this piece. Okay, so all that I have left there, I'd have a 9 minus something. And what will be left over here? I'm going to use green to demonstrate this. So when this whole thing is multiplied to the second bit, this 9 will cancel, leaving me with an x plus 3. Okay, and then on the bottom, of course, we're going to have an x, and we're going to have an x plus 3 squared times 9. Okay, so what I'm going to do right now is make sure you're good to there, and I'm going to skip just to the next slide and catch up with the question. Okay, so what we just did, Okay, so what we just did here is we multiplied top and bottom by x plus 3 squared and 9, and that's where we get to this line here. The next thing that we did, which I didn't write down, some of you may need this, is look, we just need to expand the top out. So on the top, it's going to be 9 minus, put brackets around here, x squared plus 6x plus 9. Okay, and then on the bottom, we're going to still have all that bottom stuff. Okay, now what we're trying to do is we're hoping to get rid of that x. This x, if we can cancel out that x, then there's a limit. If we can't cancel it out, there's no limit. Okay, so we did that. When we apply this negative through, we get this line right here. Do you notice anything? What cancels? I hope you can see that this 9 with this 9 cancels. And now we have negative x squared minus 6x over x. Some of us might go, hey, I could factor the top. And you don't need to factor the top, but watch what happens and see what I'm left with. Do you notice here I'm going to have this, and then I'm going to have on the bottom 9x, and I'm going to have this stuff squared. You should be cheering for me if I'm doing this all with the mouse. It is not fun. It's way easier with pencil. Okay, notice that this x and this x cancel. So all I'm going to have on top is negative x plus 6. And then on the bottom, I'm going to have 9 times all this stuff. Now I can put 0 in. I can put 0 in right there, and I can put 0 in there without any problem. So it's going to be basically negative 6 on top. And this is going to be 3 squared is 9 times 9 is 81. I'm going to cancel all this out and help you see what we did. So we canceled out the x's, and when you put the 0 in there, it's just going to be negative 6 over 9 times 9 squared, which is 81. So obviously you can see this is really tricky. The graph of this sucker, which I wouldn't expect any of you to know, looks like this. And when x equals 0, there's an empty set. But we can see that as x approaches 0 from both sides, that it definitely approaches a value, and that value is negative 6 over 81. Okay, one more challenge. This is challenge 5, and definitely a tricky one. This one says determine the value. What do you think we're going to do? On the first 2 days in calculus, we did some intro skills, and you just don't know that it's something that we try yet. But what I'm going to do here is first put the 0 in, and I'm going to go, oh my gosh, there is no limit to this because it's something over 0. But wait, there's something else we could try first. I'm going to multiply top and bottom by the conjugate. And this isn't obvious to you yet. This is a new skill. In the past, you've only rationalized when someone told you to. Okay, but we are in the big leagues now, and that's a skill. It's kind of like reducing fractions. It's, hey, I wonder if I could get rid of radicals. I wonder if that would help out at all. Notice I made a little mistake. That should be a plus. Okay, watch what happens when we do that. We are going to expand this out. This is going to be a difference of squares. So that's going to be 4 minus x subtract 4. So it's this guy times this. Remember, this is going to be a positive version. This will be the minus version. They'll cancel. Negative 2 times 4 is negative 4. And then on the bottom, what we're going to have is we're going to have that x with the conjugate business. Okay, and I know this is a lot to look at. And I also just was realizing I need to have this limit there. If you don't have the limit, you don't have the problem. The problem. Okay, so that limit is part of the operation and needs to be there. Now, look what cancels. This will cancel with this. So now we have negative x over x. Perfect. That's going to cancel. So that'll cancel. And I'll just be left with a negative 1 up here. Let's catch up on the next slide and you can see what we have. Okay, so we multiplied top and bottom by the conjugate. That's how we got from to here. And then we simplified. That's how we got to here. Must have made a silly on the back page because that is a positive x. Those x's will cancel. So now all I have to do is sneak 0 in for x as I apply the limit. And when I do that, it's just going to be 1 over 4 because the square root of 4 is 2 plus 2 is 4. So the limit is 1/4. This is what the graph looks like. Notice that there is an empty set at 0 because there's nothing there. But as we approach 0 from both sides, it does approach a limit. And there you go. So obviously super tricky, but you are now prepared to try. I think it's 5 and 6 today, pages 5 and 6. This is an older version, so make sure you're looking at 5 and 6. Hope the video